So let's take a look. So number 3, so here's the setup for number 3 just in general. Suppose you're swimming along a path described by the following. So our path that we are swimming along is, wow, let me move this closer to myself here. Okay, that's better. Cool. Is, let's see here, x equals cosine of 2t. And y equal to 3t squared plus 1. Where t is time. And the water temperature, so temperature, is given by capital T equal to x, y minus e to the y minus 3x. Ignore units. Okay. So let's find parts A and B just because it's probably going to help us figure out part B. So part A asks us to find the partial derivatives. First, del t del x. So let's just find that. So if we look at t, capital T, and take the partial with respect to x, that's going to be 1 times y. Derivative e to the y is e to the y. Derivative 3x is so close, but not quite. Oh, no, you're totally right. I'm totally wrong. Oh, I'm making mistakes. I was doing y, not x, or I was kind of doing it wrong. That's the real answer. I was doing it wrong. What should it add? So let's try this again. We were good to go on the xy portion here, but then somehow I saw a different variable. What should the derivative of e to the y actually be? Call me out. I feel like, unfortunately, as I've gotten older, I tend to make a few more mistakes here and there. So that's just the way it is, unfortunately. If you see me making a mistake, you're probably right. I'm probably making a small error. Let me know. I'm happy to fix it. I will not be offended. I know. So yes, 3, right on. So del t del x is y minus 3. Now they're just asking us to find, or are they asking us to, oh, what do they measure? Okay, so when you look at what this measures, you should always think of, oh, we're thinking about how the top thing is changing as the bottom thing is changing. So what this measures is, this measures how temperature changes, specifically as x increases. So you're asking, as x gets larger, how is temperature changing? That's what your derivatives measure in general, right? How the top thing changes as the bottom thing specifically increases. All right, so let's look at the other one, which is dx d little t. Okay, so then dx d little t, that's going to be the derivative of cosine of 2t. That's going to be negative sine of 2t times t. Sorry, times, wow, brain. Times 2. Holy smokes. Problem with t and 2 is they like sound the same in your head. So the answer to this question, the second part, like what does this measure? I'm really going to just say the same thing, just replacing what the things are. Meaning, instead of saying how temp changes as x increases, I'm now going to replace the temperature with the top thing. I'm saying how x changes as exactly. So this is going to be how x changes as time increases. Okay. Second part, find the rate of change in temperature that you experience over time. You can leave your answer as a mix of x, y, and t. So what are they asking us to find here? How temperature changes over time. Right, but so yes, you're right, the chain rule. Specifically, like if I was just thinking about what they're asking and saying, they're asking how temperature changes over time. So they're asking for a derivative. Specifically, how temperature changes with respect to time. And then you're totally right. We're going to have to use the chain rule. So probably need some more room here. This is the short example and practice in the files. Oh, it's not available. I found it by looking in. Yeah, I think I looked in the course modules. Oh, actually, I'm in my own thing. Let's see. Let me take a look here. Let me see how I found it. That's my class, not his class. Sorry, 1 second. Wow, there's so many classes. Okay. Let's see. I probably went down to modules. So I went to modules and then I scrolled down and I think I clicked on short tests in the first large module, welcome and syllabus. There's one that says short tests, parentheses, midterms. Then in there, nope, that's not where I went. That's where I thought I went. Where else can we get it?
Scroll all the way down to
Okay. Oh yeah, so if we go to week 4, is it short test logistics? I found it under, great, you found it. Okay, good. Now I need to know. Okay, so it's somewhere in there. So we're being asked to find dt. So we're going to write temperature as a function of, well, it's a function of x, but you can't see that. The function of x and y, and then x and y are both functions of t. So we're going to do the usual chain rule thing. We're going to find del t as all the paths that get to from capital T to little t. So del capital T del x times del x del t, which we already did, but then we also have to add on del t del y times del y. So, okay, this is just a kind of a lot of bookkeeping here. So let's not repeat the work we've already done, right? If you've already found del t del x, you should just use that. Erica, question? Say that one more time. Oh, you're right. You're right. So, I mean, it's not a huge deal, but you are right. I should actually be writing this as dt because t singly depends on the variable t at the very base level. Yeah, good point. So this would, but so I should say, right, this is del t del x. This is dx dt. This is del t del y. This is dy dt. It's not a huge deal, but you are right. It's a good point. So let's see. So del t del x is y minus 3. Dx dt is negative sine of 2t times 2. Plus now del t del y. So let's be careful. Del t del y is going to be x minus e to the y. I think that's it. And you guys check my work. Okay. Dy dt is going to be what? Yeah. And then I don't think they're asking us to find any particular point, so that's our answer. Now, okay. Well, I was going to say, if they were going to ask us to find another point, you would plug in t equal to whatever and find x, y. But they are asking us to do that. Let's go and do it. So part C here says, when t equals 1, are we experiencing an increase or decrease? So is temperature increasing or decreasing? Meaning, is our derivative positive or negative? So we have to do a couple things. We could write this all in terms of t. I find that to be tedious. Question. Thanks. Appreciate it. So the difference between the del and the d is that we say dt, d whatever, or like for if something's a function of one variable. So if I have, way back in the day, if I have y equal to x squared plus 7x, I'm going to say the derivative of y is dy dx. Yes, of course, because y only depends on one variable. On the other hand, if I have z equal to x cubed plus y squared, and I start finding partial derivatives, I'm going to say del z del x is equal to 3x squared, and del z del y is equal to 2y. We use the del notation if your function is a function of more than one variable. And we use the d notation if your function is a function of just one variable. And so the reason it was pointed out to me that I should be using a dt here is because although t does depend on x and y, at the very lowest level, t only depends on the single variable lowercase t. That's why we're writing, or should have been writing, dt here. I'm writing del t del x because t depends on x and y. So I'm taking a partial there and a partial there. I'm writing dx dt and dy dt because both x and y only depend on the variable t. So it's just a difference. So again, I'll point out, one, you can make them look similar. No one's really going to be checking that closely to see if you write d or del. Like if you wrote del every time or d every time, I can't guarantee it, but probably would not matter. No one would probably ever notice. But that is why. You write del if it's a function of more than one variable. You write d if it's a function of one variable. So here we could go and we could go back and rewrite y equals 3t squared plus 1 and x equals cosine of 2t. What I would rather do is find out what I'm going to get when I plug in t equals 1. So if I know that x equals cosine of 2t and y equals 3t squared plus 1, if I plug in t equals 1, I'm going to get x equals cosine of 2, which is not a lovely number, but it is what it is. I'm going to get y equal to 3 plus 1, which is 4. So that's what I'm going to jam into this function when I start doing things. So I'm going to get that dt, problem is my d's are sloppy already, so they kind of look like devils, is going to be y, which is 4, minus 3, times negative sine of 2 times 2. Okay, that seems weird also, but it is. Plus x, which is cosine of 2, minus e to the y, which is e to the 4, times 6 times t, 6 times 1. All right, and our job is to determine if this is positive or negative, which seems like not a very kind question, I will say. Like if I was asking this, I might try to make it a little more obvious. But let's figure it out. So I've got 4 minus 3, which is 1. 1 times 2 is negative 2. So I've got a negative 2 sine of 2 plus, yeesh, all right, 6 times cosine of 2 minus e to the 4. I have to assume you're not allowed to use calculators on this. You are? Okay, so if you're allowed to use a calculator, you can throw this in your calculator and see it's negative. Now, if you're not allowed to use a calculator, here's what you should know. Cosine and sine, always between. Right. So I'm just going to pretend for a moment that's 1. And that's 1. Not because that's generally what I would do, because here, e to the 4th is a big number. That's not quite 3 to the 4th, but it's not far from it. It's definitely in the range of 60, 70, or 80, somewhere around there. That's pretty big. Cosine of 2, between 1 and negative 1, minus, let's say 60, that's going to be like negative 60. Times 6, that's like negative 360. And then you add this on, which is again between 1 and negative 1, or multiplied by 2, between 2 and negative 2. This is for sure, this is very negative right here. This is for sure a negative number, which means that the temperature is increasing or decreasing. Right. So we would say that since dt is negative, that's the same as capital T decreasing. But these numbers are not particularly easy to identify whether or not the overall thing is positive or negative without doing a little bit of inspection there. So this is not a bad question. Like, I like this question. I think it's asking you to do a lot of things that make sense. It's asking you to find some partial derivatives and then use the chain rule to find the derivative. Well, he didn't explicitly say use the chain rule. It was definitely implicit there. And then finally plugging it in to see if this thing is positive, negative, and using some interpretation there. So yeah, I think a good question. Yeah. So if it's asking if what's increasing or decreasing. Right, so they asked if the temperature was increasing or decreasing, and we determined if what was positive or negative. Right, so if the temperature is increasing, its derivative should be positive, and if the temperature is decreasing, its derivative should be negative. So we looked at the derivative because that's all we knew, found that it was negative, and then said, oh, since the derivative is negative, t itself is decreasing. And that's generally true, right? If a function is increasing, its derivative is positive. And if your function is decreasing, its derivative is negative. And vice versa. So basically, if you know one, you know the other. Other questions about this question? I think we're pretty much got it. So sure. Other questions from the short practice exam? Yeah. Okay. Okay, that one's still, yeah, that one's a good one. Yeah. All right. Sure.
The worksheet,
Mhm.
worksheet one.
Yes.
from my class,
Sure.
We did it by
Oh,
setting it equal to 0, but I'm just confused with the difference between this one.
right.
one
And, and unfortunately, it's a very different kind of situation.
Yeah.
But you're not, you have the right idea still.
You wanna,
No, I'm good. Yeah. So here's the deal. If my function, I'm gonna go off a little bit. We'll come back around to 1C. So if my function, let's say, I don't know, f of xy was equal to something like, but maybe not exactly, the natural log of 9 minus x squared minus 4y squared. Seeing that, I am almost 100% positive my level curves are either going to be circles or something kind of circular. They're not exactly going to be circles because x squared and y squared don't have the same coefficient. Right? If it was minus x squared minus y squared, circles all day. If it's minus x squared minus 4y squared, instead of circles, we're going to get not quite circles, squash circles, aka ovals. So if you have x squared and y squared with the same sign, but different coefficients, you're going to get ovals instead of circles. Let's see how. So here, if I wanted to find my level curves, we would take our function and just set it equal to a constant. I'm going to pick just the general constant c instead of picking a specific value. So I'm going to say, okay, natural log of 9 minus x squared minus 4y squared equals a constant. And then we're going to try and make it look like an equation we know how to deal with. So I'm going to e both sides. So I'm going to get e to the natural log of stuff equals e to the c. Still a constant, just a new constant. And then 9 minus x squared minus 4y squared equals e to the constant. And then we're going to try and get x squared plus y squared on the same side. So I'm going to bring x squared and 4y squared to the right, e to the c to the left. So I have 9 minus e to the c equal to positive x squared plus 4y squared. And then typically, that's gross. Yeah, these are not nice numbers, such as life. Typically, when you're trying to write the equation of an ellipse, you want it to be equal to 1. So I'm going to divide everything by 9 minus e to the c. Okay, it's not my favorite, but we're going to get x squared divided by 9 minus e to the c plus 4y squared over 9 minus e to the c equal to 1. So it's an ellipse. It's a terrible ellipse. It's an ellipse where I never remember the words for the name. Like an ellipse, there's the two axes, and one's like the longer axis and one's the shorter axis. But there's like a name for them. It's like the transverse axis and the something other axis. I don't remember. But what I do know is this is an ellipse. And I know that the x-intercepts are going to be plus or minus the square root of 9 minus e to the c, comma 0. And I know that the y-intercepts are going to be, so what I'm really thinking of is just setting x equal to 0 to find the y-intercepts. If I set x equal to 0, that whole term goes away, and I'm left with this. So if I solve that equal to 0, just to show the work a little bit more, I've got, sorry, equal to 1, not equal to 0. I'm saying not equal to 0. 4y squared over 9 minus e to the c equal to 1. So y squared equals 9 minus e to the c over 4. And y equals plus or minus the square root of all of that. So again, not particularly lovely, but the point of this is more that you can isolate your equation in a way so it looks like something relatively familiar. So here's my words of advice when you have to do this level curve kind of thing. You're trying to find what your level curves look like, look for one of two things. Either you're going to see x squared plus y squared, or maybe minus x squared minus y squared. But somewhere you're going to be able to get x squared plus y squared on one side equal to some other stuff. And maybe you'll have something crappy like this where it's an ellipse instead of a circle. Probably not in a test though. If I had to bet, I would bet you'd have a circle versus an ellipse. That's what I'm hoping. The other thing that might happen is not that. Meaning you're just going to have x's and y's, and then your usual best option is to try and solve for y. So let's take a look at this other question here from the practice test. Specifically, let's look at part C. Yeah, and we can talk about parts A and B too if you guys want. But let's look at part C. So for part C, we have f of xy equal to x plus 2y over y minus 2x. And we're going to set that equal to a constant. I will point out, we can go back and talk about this in a minute, but the range of this function is everything. You get all possible z values. So there isn't anything c wouldn't be allowed to equal. But generally, whenever you're picking your level curve values, if you're actually picking real numbers, those numbers have to be in the range because you're setting the function equal to it. So here, I'm going to try and solve this for y. All right, so usually getting rid of the denominator is a good first step. So x plus 2y equals c times y minus 2x. And then distributing the c, so I have x plus 2y equals c times y minus 2 times c times x. And then we're trying to solve for y, so we want to bring all the y's to the same side. I'm going to bring them to the right just to make it more things positive, but either side is fine. So I'm going to have x's on the left, x plus 2cx equal to y's on the right, c times y minus 2y. Factor out a y. And I think I'm going to factor out an x2 just because it'll help me see what's going on here. And then divide both sides by the coefficient of y. So y equals, I'm going to write it like this, x times 1 plus 2c over c minus 2x, and then factor out the x, and write it as 1 plus 2c over c minus 2 times x. Or y equals some constant times x. Now, a couple things to see here. Thing one, looking at this, what is the only thing, at least in this situation, that c is not allowed to equal? 2. 2 is a problem. So let's go back and deal with that problem real quick. Question. Typically, so again, you're either going to try and solve for y, or you're going to try to solve for x squared plus y squared. This is usually what's going to happen. It's not to say that other things couldn't happen. Like you can totally have a situation where you had x squared minus y squared, and that would be a hyperbola, but we just don't typically see examples of that. So usually we're trying to get x squared plus y squared or y equals, because we know how to graph y equals a thing. We know how to graph x squared plus y squared equals a thing.
I have 2 questions. One, I thought you said that since the range is everything, should be.
You're right. You're totally right. So here's what I'm going to say. If we look at this, if we did set, so first of all, this kind of equation, what kind of, if I pick c equal to not 2, so let's pick a couple of values here just to see. If I pick c equal to 1, for example, what am I going to get for my equation here? Y equals what? I think 3 over. The 3 over -1, which is, so what kind of graph is that? A straight line, specifically that goes to the origin. And if you pick another value, if you pick a different value for c, like c equal to, I don't know, c equal to 3, I'm going to get y equal to 1 plus 6 is 7 over 7x. So you can notice here, after a couple of values for c, that no matter what value for c you pick, except for c equal to 2, you're always going to get a straight line through the origin. So now let me ask you, if we did pick c equals 2 over here, what kind of slope are we getting? Right, because this is the slope, right? The thing multiplying x is the slope. So if I plugged in c equals 2, we'd be having a slope of not 0, undefined, right? 0 would be 0 over something. We have something over 0, which is undefined. What kind of lines have an undefined slope? That's a 0 slope. You're getting that. So the other kind, right? Not the horizontal, but the vertical line. So vertical lines have a horizontal. Vertical lines have an undefined. So you can't really just say that you're for sure going to get that though by plugging in c equals 2. So let's go back to the beginning real quick just to see what happens if c is equal to 2. So you're totally right. C can be anything, but c equal to 2 is a problem here. So I'm going to go back to the beginning. Say, okay, well, if I had c equal to 2, well, this first step is okay. So let's say I have x plus 2y equal to 2. times y minus 2x. And check out what happens. We have x plus 2y equal to 2y minus 4x. And what's going to happen to the y's? Yeah, 2y minus 2y is 0. So I'm left with x plus 4x. And that sounds like 5x equal to 0. And now I've got the vertical line that goes to the origin, x equal to 0. So that's the level curve specifically with C equals 2.
So if I, because like the way I put this question is, I set, so like I put 3.
Sure.
But I set it all equal to that instead of finding the general.
Right. So the thing I like about finding the general formula is that I guess doing 3 is probably enough to kind of see what's going to happen in general, but maybe it's not. Whereas doing it this way, I can look at this and be like, oh, I know, except for C equals 2, every level curve is going to be a straight line that goes through the origin. And so is C equals 2, it's going to be a vertical line. So I think doing it the general way is more, it allows you to see what's happening faster.
Doing C equals to 2 and drawing that vertical line on top would be correct.
Yeah. So if I was going to start drawing my level curves, I would probably try to draw them in a way that didn't look like crap. So I might use something like, well, no, we should do it. Like you actually have to draw them probably. So, but if I was going to draw some level curves, so for C equals 1, I've got y equals negative 3x. Okay, so color pen time. See how it works. So here's C equals 1. That's pretty good. That seems like a reasonable y equals negative 3x. And I'm not going to draw it again, but here's C equal to 0. Sorry, C equal to 2. Apologies. And then we go right. We have an even steeper line at C equal to 3. So here's C equal to 3. I might go, well, I'm going to go a couple more just to a couple more. So let's do C equal to 0. So if C equals 0, I'm going to get 1 plus 0 over negative 2. So I'm going to get y equals negative 1/2 x. So that's going to be a much less steep line. Not like that. And I guess I could go C equal to 4, but that's going to be really big. Well, actually, no, maybe not. C equal to 4 is going to give us 1 plus 8, which is 9 over 2. So it's going to give us y equal to 9/2 x, which is 4.5x. So it's going to be even steeper than that one. Ugh, I don't love that. Yes. I can even zoom in a bit. So that's what's going on there. So you've got the way I kind of imagine this three-dimensional surface, well, I don't know if it's exactly right, is it kind of maybe kind of spiral staircasey, like, or maybe like a DNA kind of helix thing. It might look kind of like that. I think even though it's not being asked, I think it's worth our time just to look at it very quickly, because I do think it's good to see what's going on. Oops. Oh wow, geez, okay, that's how, why am I getting, I don't like this double video thing. That's terrible. Sorry. So let's go ahead and look at the graph just for a moment. Let me just write it here so I don't mess it up. So let's see, we had z equal to x plus 2y over y minus 2x. Now I know you won't be able to do this during an exam. It doesn't mean it's not worth seeing anyway. Oh yeah, totally looks like what I was kind of thinking. So if you take a look at this, you can kind of see, yeah, it looks like the higher up you go, your level curve is just a straight line. So just to kind of make it a little maybe easier to see, let's go like to z equals 2. So if you look there, oh yeah, that surface is definitely being cut, or that plane is cutting the surface in exactly a straight line, like y equals, oh, that's actually x equals 0, right? That's exactly x equals 0. See, I picked the wrong one. Let's pick z equals 1. So that one also, right, is being cut You can kind of see maybe, it's a little dicey. You can kind of see, like right there's the equation of the line. But it is a line that's cutting that surface. Erica. No, your level curves can be anything. They can be lines, so they are typically lines, circles, but they can really be anything. They can be parabolas, right? Your function could be something like f. Oops, you might want to see what I'm writing. Your function could be something like f of x comma y equal to y minus x squared. That could be your function. And then as you pick larger and larger values, and so first of all, I should point out domain everything, meaning the entire xy plane, not all real numbers. So just to be super clear, domain entire plane, or set of all x, y such that x and y are real. And the range would also be everything. You can totally get every possible real number in your range there. Let x equal 0, let y be anything you want it to be. There you go, you've got the entire range. So then our level curves here, well, again, I'm going to do the same thing I did before. I'm going to pick a constant value, just c, and say c equals y minus x squared. And since there isn't a nice x squared plus y squared to isolate, I'm going to do the other thing, which is solve for y. So I'm going to say, okay, y equals x squared plus c. So then when I start graphing the level curves, I'm just going to get parabolas that sit essentially on top of each other. So for example, if c equals 0, I'm going to get y equals x squared. Okay, this is where the graphing has to be pretty careful because they shouldn't cross each other. My parabola is kind of extra big. And then for c equals 1, we're going to get y equals x squared plus 1, which is just shifting the parabola up by 1. And so on, and so on, and so on. Right, for c equals 2, we're going to get y equals x squared plus 2. Right? Not particularly exciting. So the higher up we go, the further up the y-axis they move. So if you were graphing this in 3D, you would kind of on the floor, you would have a parabola that opened towards the y-axis, right? Assuming, right, that's y, that's z, that's x, that's you. Your parabola would open that way, and then as you go up your surface, you're going to be kind of curving this way. So your parabola would move further to your right as you move higher, higher, higher. Yes.
Would it be fair to say that possible level curves that we could see are parabolas, ovals, circles, and then lines?
I would say that's a little too limiting, because so it's really technically what you say is the level curves you can see can be anything. The level curves you are likely to see are circles, maybe ovals, lines, possibly parabolas.
Because like I'm just afraid that I'll show up and then I
Sure.
won't know.
Right.
Recognize the function that's one of those.
Right. So again, it might not be easy to see exactly what it is, but I would go back to the default of either look for x squared plus y squared or look for solving for y. Yes. Yeah.
I have a question about the range for
Sure. Let me actually, there's a question here. So the question asks you to sketch 3 level curves. Can you pick any 3 values of c? Yes, you totally can. In this case, with drawing c equal to 2 level curve, c equal to 2 is a valid level curve. Any choice for c that is in your range is valid. This one just looks a little different because it's the unique choice, but it's still a good choice. Sorry, go ahead. It is often the so that's actually a good question. How do you actually, for this particular example, how do you justify to yourself that the range is what it is? Because it's not always super easy. When you have an x squared plus y squared, it's very easy to deal with the fact that we know that x squared plus y squared is always greater than or equal to 0. So just to kind of backtrack for a second, if our function, for example, was, I'm going to make something fairly easy. the natural log of x squared. Sorry, I want negative x squared minus y squared plus 25. If that were my function, here's how I'd find the domain in the range. And then we'll go back to the other one. So here, domain, super not terrible. You're going to have all your stuff. 25 minus x squared minus y squared has to be greater than 0 because you can't take the log of 0 or negative. So then we isolate x squared and y squared, and we get x squared plus y squared to be less than 25. So that's everything inside the circle of radius 5, not including the border. You might want you to graph it. If you're going to graph it, it looks like this. You draw your circle dashed. It's got a radius of 5. And then you color it in. That's our domain for this particular problem. The range is also not terrible. And here's why the range isn't terrible here. We also know that if I have this domain, x squared plus y squared is less than 25. There's also something else that's great that you get to say about x squared plus y squared. And that is that x squared plus y squared is greater than or equal to 0, no matter what. X squared is greater than or equal to 0, y squared is greater than or equal to 0, and the other greater than 0. So then the idea here is you can use this to kind of figure out what's going on here. So if this is true that x squared plus y squared is bigger than or equal to 0 and less than 25, then 25 minus x squared plus y squared. Well, if x squared plus y squared is between 0 and 25, then 25 minus it, well, 25 minus 0 is 25. And 25 minus 25 is 0. So if our thing is between 0 and 25, and we're doing 25 minus that thing, it's still between 0 and 25. Notice, though, a slight change. Here, x squared plus y squared is bigger than or equal to 0 and strictly less than 25. 25 minus that is less than or equal to 25 because this could equal 0, and 25 minus 0 is 25. And it is strictly greater than 0 because 25 minus almost 25 will almost get you to 0, which makes sense because if we're taking the natural log of this, we can't take the natural log of 0. So we don't want to be getting 0. Okay, so now give me, what's that? Sure, we'll come back again. So now if I was going to deal with this, I would take the natural log of everything. So natural log of 25 is no big deal. Natural log of this is what we want in the middle. And now I'm going to ask a question, which is kind of not the best question ever, but it is the question asked. What's the, I don't want to say this, what's the natural log of 0? The natural log of 1 is 0. It's undefined, but in what kind of way? So let me ask you all, picture in your mind for a moment the graph of natural log of x. And ask yourself, okay, as we get closer and closer and closer to x being 0, which direction is the function going? Negative infinity. You're going down, down, down to negative infinity because the graph looks like this. So even though it's not a great way to say it, the quote unquote natural log of 0, or what happens to the natural log function as the input gets really close to 0, is that you're going towards negative infinity. So here the range of this function would be negative infinity up to natural log of 25 with a bracket. So there was a question about the level curves from before.
Yeah. Like, you know, for example, like this, I forgot what we're doing. And you're going to like use half of the circle.
Oh, like your domain was only half of the circle?
Something like that. Is there any time like
No, there are so let me think for a second here. Yeah. I feel like less likely for the level curves, but I guess you could if you're getting, I don't know. So what I would say is what I feel like you might kind of be asking, although I'm not 100% sure, is if we had something like this, where you had, say, let's say we had the same function that I had before, I have f of x, y, still equal to the natural log of negative x squared minus y squared plus 25. But then I've decided to add on the square root of y. So now, in addition to this requirement that we're living inside this circle, what else has to be true about y? Right, y has to be greater than or equal to 0. So the domain for this one would look kind of even extra funky. The domain here would be, I'm still missing the circle, but I want everything inside of it, but I don't want y to be negative. So I'm going to get this border here and all the stuff in here. That would be our domain for that function. The level curves, no. Yeah, I guess the level curves would be the level curves would be weird. They'd be weird. They wouldn't necessarily be circles because you've got this whole other y thing going on here. But yeah, I don't know. I don't have a good answer to your question without giving it more thought. Let's get to the other part of this, which was actually talking about the level, the domain and range for the other function we actually want to talk about. The whole. Do you have a question about this? Yeah. Okay.
Why did the greater than the function that too small?
So because what I'm saying is, I have, so we could really do all the work if we wanted to. So I was trying to make it a little easier to kind of see what's happening by saying, oh, if this is between 0 and 25, then 25 minus it is also between 0 and 25. But 25 minus actually equal to 0 gives you 25, and 25 minus almost 25 gives you almost 0. But the kind of the longer way to see that is to say, okay, so check this out. Yeah. So if we take this inequality, you really can manipulate it until you get what you want. So I really want that. So I'm going to multiply everything by -1. So -0 bigger than or equal to negative x squared minus y squared bigger than -25. Because I multiplied by a negative, that changes the direction of the inequality. And then I want to also get a plus 25. So I'm going to add 25 to everything. So 25 minus 0 bigger than or equal to 25 minus x squared minus y squared bigger than 25 minus 25. So now I've got exactly 25 minus x squared minus y squared is less than or equal to 25 and is bigger than but not equal to 0. So that's kind of the more showing all the work way of saying that, oh yeah, we really are getting this inequality. And then taking the natural log. What I wanted to get to?
Yeah.
Because that's what's inside the function. So I know I'm starting with this because that's my domain. Well, I should really say that's my domain, but that has to be true, right? It always has to be true that x squared plus y squared is greater than or equal to 0. So then I said, oh, I have this, but I want that. So I asked myself, what do I need to do to change this middle part into that? Well, I have x squared plus y squared. I want negative x squared minus y squared. So I multiply by -1. But I can't just do it to the middle part. I have to do it to all the parts. And then now I have negative x squared minus y squared, but I want to add on 25. So I add 25 to all the parts. And then that gets me to the middle part being the same as that. Oops, you actually can't quite see that. And then at the end, I would take the natural log of it, just like I did. So natural log of all this is between those two things.
On the left side of the range or negative ranges, is it right to just say that, oh, the smallest thing that ln can happen is 0, then ln is 0, or should I
would say you can, the smallest thing, so there really isn't the smallest thing natural log can have in it, because effectively you can't take the natural log of 0. But really what you can say is, as the input for natural log gets smaller and smaller, the output gets more and more negative. But yes, you can also say inside your own head quietly, natural log of 0 is negative. Just don't tell. So the circle, this circle is the domain for this function. No, we didn't graph a level curve at all here. Well, so here's what I want to emphasize. Domain for functions of two variables is going to be some area in the plane. The range is still going to be something just on the number line. So here the range is just negative infinity to the natural log of 25. So my range looks like this. It's not very exciting. Here's my range. Kind of boring. And that's always true of the range for these types of functions. The range is just some interval on the number line, whereas the domain is some space in 2 dimensions. If we were going to graph level curves, we would get circles here. We would do the whole thing where you set this equal to a constant and then try to isolate x squared plus y squared, which you would do by eing both sides and then subtracting 25 or whatever. Let's get back to the other question, because I think that's the one that might be more on your minds. Again, I can't speak to how challenging he might make a question like this. I certainly feel like the one that's on this practice short test is a relatively challenging question. At least, I don't know. To me, it feels like it is. Sorry. That's a cool graph. Let's go here. So we were looking at this one and talking about the domain and the range. So f of x comma y was equal to x plus 2y over y minus 2x. Now let's talk about the domain really quickly first. So what's not in the domain? Y equals 2x. So really all you have to do to find the domain is think about, do you have any logarithms? We don't. Do you have any square roots or even roots? We don't. Do you have any dividing by 0? Oh, we might. So we don't want to divide by 0. So we have y minus 2x not equal to 0, or essentially y not equal to 2x. So our domain is everything except for we want to exclude, the line y equals 2x. So if you had to graph the domain, I would draw the line y equals 2x dashed, and then say, great, it's everything else. There's my domain. All that except for that one. The range is harder. So it is a very, very good chance that you have some quotient like this, unless you've got some square roots or something, or some squares, it's probably going to be it. Here's how I would try to most quickly justify that to myself. I would pick x equal to a number, not 0. Well, actually, here's what I would pick x equal to 0 first, because that's always where I start. But if you pick x equal to 0, what are you going to get for y? Or what I said, what are you going to get for your function? If x is 0, I'm left with f of 0 comma y equal to 2y over, which is always, unless y is 0, but okay, we're not going to. So great, you got 2 in the range, and that's it so far. So now I'm going to make a different choice because that choice didn't pan out. Usually what ends up happening is something like the following. So instead of picking x equal to 0, although it's totally fine to have picked x equal to 0, it got us that 2 was in the range, which might be hard to see later on. Let's pick x equal to the next easiest number, like 1. Actually, no, that's really simple. So I pick x equal to 1. My function is f of 1 comma y, and that's going to be 1 plus 2y over y minus 2. And now the question is, can you get that to equal any number you want? Well, here's what I'm going to add. And so this might feel weird. I'm going to set this equal to any number I want. And I'm going to try and see if I can always find a y to get any number I want. So literally, I'm going to work through the same work I would have done to have done my level curves. Except a little bit different because I'm not. So, I mean, technically, maybe what sure, okay. This is what I would do. So I'm going to solve for y. So 1 plus 2y equals cy minus 2c, right? Multiply that over. Bringing the y's to the right, cy minus 2y equals 1 plus 2c. So y times c minus 2 equals 1 plus 2c. So y equals 1 plus 2c over c minus 2. So let me ask you, if I set this function equal to any c, can I always find a y? Or a better question is there any value of c that's problematic? 2. Okay, aside from c equal to 2, because we've already said that 2 we can get. So aside from c equal to 2, is there any other value of c you can't get? No, I can pick c equal to 7. And I can say, well, if c is 7, y had better be 1 plus 2 times 7 over 7 minus 2. That works. So if you do this kind of thing where you set your function equal to a constant and solve for y, you can kind of see, oh, I'm going to get. Now, what I should point out here is really this is the same work as just kind of what we did before, where we did this. Right? We could have said here, well, I'm setting this function equal to c, and I'm asking, can I get every value of c? And it looks like, I mean, if I set x equal to 1, for example, c can be anything except for 2. So try not to do the same work twice. Like, I'm doing it twice to show you what's going on. But really, like when I'm trying to find the range, I'm really just asking what kind of level curves am I allowed to have, or are my level curves allowed to equal? So I'm setting this function equal to a number, then it's kind of asking, can I get there?
What if you didn't like going through picking the numbers? What if you never did x equals 0 and you found out that the domain can't be 2 and you just went to
You mean the range?
the other range, sorry, and then you just went to finding like the work with c? How would you check that c can't equal 2?
How I check this? You can't equal to?
You can't.
Okay, wow, fair enough. So okay, good question. So let's say I did all this. I picked x equal to 1, and then I said that, oh well, if x is 1, I can get any value of c except for 2. Right, that's what we're saying. Right. So then I need to check, right? Because maybe I can't, right? I only checked kind of one thing. I said, well, if x is 1, then I get everything with c equal to 2. So now let's go and check, see, can I also get 2? So then what we're going to do is we're going to set, and we've already done this before, but I'm going to set the function equal to the one thing I couldn't get. And then I'm going to try and figure out, is there a solution to this?
Whether or not you can
If you can or cannot be in the range. So far, ignoring this work I did up here that you can't see anyway, what I've got here is, oh, my range so far can be anything except for 2. Because my function of 1 comma y can equal any c value except for c equals 2. So now we're going to check, can my function actually equal 2 as well? So not just no, oops, and I made a little mistake here. That should be y minus 2x, sorry. Now, we could, like, I guessed it before, right? I guessed x equals 0 and I got the thing. So let's pretend like we didn't know that. So I'm just trying to figure out how I'm going to do this. Well, I'm going to multiply both sides by y minus 2x. So x plus 2y equals 2y minus 4x. So then the 2y's cancel. And I'm getting 5x equal to 0. So I'm getting x equal to 0. So then I go back and double check and say, well, if I plug in x equal to 0, does it work? Does 0 plus 2y over y minus 0 equal 2? Yes, as long as y is not 0. Right? Y couldn't be 0 here because 0 plus 0 over 0 minus 0 is not a function. So this equals 2 or y not equal to 0. So for example, if you have x equal to 0 and y equal to pick any number you like, that'll give you an output value of 2. F of 0 comma 5 is equal to 0 plus 10, 5 minus 0, which is 2. Check. So that's what you would do. If any values were missing, you would then go back and see, can I actually still find a way to get that? And usually for things that look weird like this, typically your answer is, yeah, you get it. It's just kind of, usually there's one value that might be a pain to kind of check. Oh, sorry, there is again, apologies. Someone asked if I can go over question number 9 on the midterm practice. Yeah, okay, I imagine someone was going to ask that one. Yeah, we got time. Consider the map. So just in case, I assume everyone's seen it, but just in case everyone hasn't seen it, right? Here's what it looks like. It says, consider the contour map of z equal to f of x, y below. Notice our level curves are lines, right? Not circles. So consider the map of z equals f of x by below. Contours for various values of z are plotted below and labeled with the corresponding value of z. Meaning the height. That's what, at least, maybe not meaning that, but definitely what I'm thinking is, oh, that's the height of my surface. It could be temperature, it could be something else, but if no one says anything, I'm thinking height. The 0.32 is marked with a dot. Great. Use the contour plot to approximate the rate of change of z at the 0.32 in the x direction. So we're asking, at this point right here, approximate the rate of change of z at the 0.32 in the direction of x. So meaning moving which way? Up, down, left, or right? Up, down, left, or right. If we're moving in the direction of x, we are moving to the right. Specifically to the right, from left to right. Because we're moving in the direction of positive x, not negative x. So if they say the x direction, they specifically mean not just horizontally, but from left to right. So yeah. So the way I would do this, since things look pretty constant, is I would say, okay, well, if I start at this point here, which is at the x value of 3, and I move over here to an x value of 5. So my run is 2. Right, I've increased x by 2. How much has z changed by? Has it increased or decreased by 1? Right. So here's what we can say. We can say that from that point, so right, we were going from, I was saying we were going from here over to here. That's our point 3, comma 2. This point here corresponds to when x is 5, and this is the z equals 2, and this is must be the z equals 3. All right, I think that's what we had. Let's double check just to make sure. Maybe. Z equals, oh, sorry, we're already on z equals 3. I apologize. And we're moving over to z equals 4. Sorry about that. Okay. And they're asking, approximate the rate of change of z. So we want to find what's the rate of change of z. In other words, what's the derivative of z with respect to the direction we are going? Or in approximation terms, what's the change in z over the change in x? So from here to here, how much did z change? From here to here, how much did x change? That's it. So typically when they're asking you to find a rate of change on a level curve graph like this, they're asking you to move from one point to another point. And the top part of your fraction is how much your level curves differ by the end one minus the beginning one. So really what I should say here is this is 4 minus 3, the end value of z minus the beginning value of z, divided by the change in the direction you're going. So the end value of x minus the beginning value of x. And just to go in the other direction for a second, just let me hold on to your question for a second. So if instead we go in the y direction, meaning, so I'm going to ask you all to point, which direction is the y direction? Up, down, left, or right? Yeah, it is exactly up, not up or down, just up, which you all did point. So from this point here, if I move in the up direction, I'm going to be heading towards this level curve, which means we would expect our function to be decreasing, right? Because the z values are going to be less. So from here to there, see if I can draw it. Why is this cursor so impossible? Okay. So, right, if I instead go to this next level curve, z equals 2, I'm going instead this way, right, up to this next point, which I maybe doesn't look right. All right. So this is the point. I think it's the point 3, comma 4. Let's double check on the graph that because my remembering could be off. So let's see, from here to kind of the next easiest place to read. Oh yeah, the coordinates are x is 3 and y is 4. And z is what? 2. Okay. So we have 3, 4, and z values 2. So if I'm trying to now find del z del y, the rate of change in the y direction, that's just the change in z over the change in y, which is going to be the change in z is the end value minus the beginning value. The change in y is the end y value minus the beginning y value, which is going to be -1/2. It makes sense that it's negative because we moved in the direction where the z values were decreasing. Let's see, was there another part of this question? Okay. Yeah, and I guess if we had gotten to the next section, he could have asked you something like, all right, what would the rate of change be if I moved in the up and to the right direction? It would be a directional grid, which will not be an test. Okay, good question. There was a question, right? You had a question? Cool. It is 2:45. We got like 15 minutes left. Are there other things we should look at? Probably, hopefully. 6. That's the wrong thing you're looking at. Maybe did it disappear? Did I lose it? For real, where did you go? Oh, there it is. Sorry, it's hiding from me. Apologies. I moved it over here. That's where it went. Yeah, let's see. So number 6. Find an equation of, so sorry, someone asked, so when we get a question like this, what should we start to look for? You should start, so if you're being asked to find what, so this question says specifically, apologies. The previous question said specifically, approximate the rate of change of z at the point in the x direction. Look at that point. You should move in the appropriate direction. So if it's the x direction, move to the right. And ask yourself, okay, if I move over to the right, you essentially want to find, I moved over to the right until I found kind of the next level curve, right? So I started here and I went, oh, if I go over to the right, I'm going to hit that next level curve there. So I look for the next level curve and be like, okay, well, my z's increased. So my change in z was 1. My x's, and the bottom thing should always be increasing. Right? If you're moving in the x direction, x should be increasing. Moving in the y direction, y should be increasing. So I looked for my change in z, which was a +1, over my change in x, which was a +2. So I'm always looking for essentially the difference in z values and the difference in whatever the input value is from one level curve to the next level curve in the appropriate direction. That's what I'm looking for. Okay. So, let's see. So question 6. Not that you're not allowed to see it. I just want to read it up here so I can see it. Find an equation of the tangent plane to the surface z equals 4 minus xy plus x natural log of x at the point 1, 4, 0. So let's write that down. They want an equation of the tangent plane to z equal to 4 minus yx plus x natural log of x at the point, I'm going to say 1, 4, 0, aka x naught, comma y naught, comma f of x naught, y naught, also known as z naught. So what I will point out here is that to do this question, you really do have to kind of have remembered the equation of the tangent plane formula. There's not, I mean, you could derive it, but that's not the best use of your time. So here's the equation of a tangent plane, also known as the linearization of a function. The equation of a tangent plane is going to be given by z equal to f of x naught comma y naught plus the partial with respect to x at x naught y naught times x minus x naught plus the partial with respect to y at x naught y naught times y minus y naught. I should point out everything in this equation is a real number except for that's a variable, that's a variable, that's a variable. Question? Totally, exactly, yes. Cool. So if I was doing this, I would probably take a moment and actually find the partials first. Oh, question, Erica? Yep, right, because if I just brought this over to the other side, it's totally Z minus Z. Yep, you can totally see it that way as well. There's lots of different ways of writing this down. This is just the way I happen to do it. But yeah, Z minus Z naught. Some people write L of XY here for the linearization. So you might also write this as L of X comma Y. That's also a perfectly fine way of doing it. So let's find our partials. So Fx is going to be the partial with respect to X, which is going to be negative Y plus, got to use the product rule here. Derivative of X is 1 times natural log of X plus X times the derivative of the natural log of X, which is 1 over X. And that's going to simplify as negative Y plus natural log of X plus 1. And then our Fy partial is going to be negative X. Then that's it, negative X. Cool, much easier. And then I would probably actually even also plug in the values. So I would say the partial with respect to X at the point 1 comma 4, X and plugging in X equal to 1, Y equal to 4 is going to be negative 4 plus natural log of 1 plus 1. Natural log of 1 is 0, so that's going to equal negative 3. Similarly, Fy at 1 comma 4 is going to be negative 1. Plugging in the X and Y values. I didn't write 140 because I'm not going to be plugging in the Z value. You could write 140. So then let's throw it all into the formula. So we're going to get Z equal to F of X naught Y naught, which is Z naught, which is just 0. But you don't actually have to do the work of plugging in 1 for X and 4 for Y to find Z because it already was done for you. You could plug in 1 for X and 4 for Y, you get 4 minus 4 plus 0, which is 0. Plus the partial with respect to X, which we just found to be equal to negative 3 times X minus the X coordinate, plus the partial with respect to Y, which we found to be negative 1 times Y minus the Y coordinate. And in my opinion, I would leave it like that, or maybe I would simplify it a little bit. I've got Z equal to negative 3 times X minus 1 minus 1 times Y minus 4. I personally don't prefer to multiply that out, but you certainly can. We can multiply it out and get Z equal to negative 3X plus 3 minus Y plus 4. And then bring all the variables to the left and say we had like 3x plus y plus z equal to 7. The reason you might want to leave it like this instead is if they then ask you to use that function to approximate something, it's usually easier to plug it in here. Kind of like question 7. So I feel like having done question 6, question 7 is also probably worth looking at. We got time. We got 8 minutes. Okay, let's look at question 7. And we'll see what I mean by this. So question 7, find a linear approximation to the function f of x comma y equal to, I'm going to write it as 20 minus x squared minus 7y squared at the point 2 comma 1. Here's what I want everyone to see before I write the rest of the question. Currently, these two questions are the same question. Different function, but the same question. Both of these questions are asking us to find the equation of the tangent plane, also known as the linearization of the surface. They're the same thing. They're going together on purpose. So when I see this, I should just say, oh, well, I'm doing the same thing. I'm going to say that my linear approximation, which I'll probably use the notation L of XY instead of Z here because that's more indicative of the linear approximation, even though it's the same, is going to be same as before. Z naught for f of x naught y naught plus the partial, oops, there's a 1/2 power there, sorry. The partial with respect to x at your point times x minus x naught plus your partial with respect to y at your point times y minus y naught. Let's actually flip it up this time and do the plugging in before we find the partials. So our z naught here, they didn't give it to us. So we actually have to find Z naught. So Z naught is going to be f of 2 comma 1, which is going to be 20 minus 2 squared minus 7 times 1 to the 1/2 power. That's 20 minus 11, which is 9 to the 1/2, which is 3. So this formula is going to look like the following. Our linearization at x comma y is going to look like Z naught plus our partial evaluated at 2 comma 1 times x minus 2 plus our partial with respect to y at 2 comma 1 times y minus our y coordinate. So all we have to do now is figure out what our partial with respect to x is, and what our partial with respect to y is, and plug in for those. So let's do that. So here's our function. Let's take its partial derivative. This is plural. So fx is going to be 1/2 times our stuff to the negative 1/2 power times the derivative of the inside stuff, which is going to be, what is the derivative of the inside stuff here? And just minus 2x, nothing else, because it's just with respect to x. So then if we plug in fx at the point 2 comma 1, now again, let's be smart and let's not do more work than we have to do. We already know that when you plug in 2 comma 1, 20 minus 4 minus 7 is going to be 9. And then 9 to the 1/2 power is going to be 3. Now be careful here. We have 9 to the negative, which is going to be 1/3 instead of 3. So we're really going to get 1/2 times 1/3 times negative 2 times x, which was 2. That's going to end up being negative 2/3. Similarly, fy is going to be 1/2 times 20 minus x squared minus 7y squared to the negative 1/2 times negative 14y. And if we plug in fy at 2 comma 1 is going to be 1/2 times, again, 1/3, right? We're just plugging into the same thing. We're getting out a 9 to the negative 1/2, which is 3 to the negative 1, which is 1/3. And then negative 14 times y is just negative 14 times 1. So that ends up simplifying as negative 7/3. And that's what's going in there and going in there. So our final linearization is L of xy equals 3 minus 2/3 times x minus 2 plus negative, I should have just written negative 7/3, sorry, times y minus 1. And now here's my point. My point is this question then asks you to approximate f of 1.96, 1.09. And the idea behind this is that you're supposed to use the linearization you just found. So the function is approximately equal to the linearization. And now here's where I want to make a strong case for you don't want to simplify this. It's much, much easier to plug in 1.96 here and do 1.96 minus 2 times 2/3, as opposed to having multiplied this whole thing out and doing something else worse. So specifically, if you're asked to actually approximate a thing, it is usually your best interest to not simplify your tangent plane or your linearization. To leave it as like this, where you have slope times x minus whatever, slope times y minus whatever, because the x minus whatever and the y minus whatever are going to be small numbers. So if I do this, I'm going to get 3 minus 2/3 times 1.96 minus 2 is negative 0.4. Sorry, negative 0.04. Apologies. And 1.09 minus 1 is 0.09. And then you could get a nicer answer if you wanted to simplify that. It's not beautiful, but question. Yeah. They'll tell you use, like, they might say, so here's maybe the least number of words you can say to ask that question. Use this function to, or no, you have to really say, you have to say, like, no, you really have to kind of say, find a linearization of this function to approximate f of, in this example, 1.96 comma 1.0. But you kind of have to say some words about using a linearization to approximate this function at this point. Question?
More about
Okay,
let's say like they ask us to do partial z over partial x
sure.
of y ln of x squared plus 2. I can repeat that.
Sure.
But I'm confused of,
So say it one more time.
yeah, so partial z over partial x of y ln x squared plus 2.
Now, let me ask you,
Because I always,
is it the partial with x of z equal to y natural log of x squared plus 2?
yeah,
Okay, so all this means is take the derivative with respect to x.
yeah, but what I always get tripped when I'm doing this on whether I drop y or not. Or like, so I always keep.
Okay, well, no, we don't always keep it. So I'm going to give you two different questions here and then we'll wrap it up. So let's say we have this versus this. So here, if I'm finding del z del x, what is the derivative of 4y? It is 0. Plus this garbage, 1 over the stuff, times the derivative of the stuff. Here, the y gets to hang out because it is multiplied by a function of x. So that's like a constant multiple. So here the derivative would be y times 1 over x squared plus 2 times 2x. The difference is the difference between this function, f of x equal to 3x squared, the derivative is 6x, versus this function, f of x is 3 plus x squared. The derivative is 0 plus 2x. So constant multiples, constants on their own have a derivative that is 0. Constant multiples stick around.
Then that because it's being multiplied by the x.
The y squared would stay. So the derivative of xy squared with respect to x would just be y squared.
So it's just the same thing. But with that.
Right. Yep. Yeah.
Thank you.
You're welcome. All right. I should head